Okay, that was a simple case. Okay, and now we have to consider the case in which the vectors do have elements. And we're going to also break this down into two more cases, depending on whether or not the first elements of x and y are identical. Okay, so the first case is, yes, they are identical. So in this case, determining whether x and y are permutation boils down to whether or not the tails of x and the tail of y are permutations of each other. And the tail of a vector is everything except the first element. So we could say that for this case, in order for the output to be a permutation of the input, the syntax that you see on the slide holds. And in particular, that says if the length of x is greater than 0, that's our special case. And our second special case was that the value in the first position of x is equal to the value of the first position in y. And the third condition is if the permutation, if the tail of x is a permutation of the tail of y, then we can conclude that in fact x and y are permutations of each other. So what we're doing now, we handled the case where they were empty vectors and said they were permutations. And in this case, if these three conditions hold, they are permutations. Okay? The other thing to note is that what we've defined here is a recursive definition. Now, I warned you before about recursive definitions often leading to cases where the definition is not meaningful. Now here, I'm going to give you a specific situation in which you are allowed to do that. And we're allowed to do that because it essentially is an inductive argument. Okay? The permutations that we're using in our definition are permutations on the tails of the input and output. Okay? And the tails are everything but the first element, and so they're shorter. And we also already have handled the case where we got down to 0 length. So we handled 0 length and we handled everything in terms of its tail. We have a well-founded induction here. And so in fact, our definition of permutation is in fact meaningful. We couldn't say that x is a permutation of y if x is a permutation of y. Okay? That wouldn't be a meaningful induction. But here, because we're shrinking it at every step, it is in fact a meaningful induction.